so we got our circle, and the center of our circle has two locations. Well, not two. It can be at any location along our Cartesian plane. But when it's at the center, or the origin, I shouldn't say the center. When it's at the origin of an xy axis, our equation is simplified. It doesn't have any left or right movement or up or down movement. When it's sitting somewhere else, we call that other place our h and k variables that define the center of our circle. So here are our two equations for circles. One of them where I'm somewhere else, not at 0, 0. And then one where I'm at 0, 0. Have you guys seen those equations before? See, I think this is the first time that you've probably seen circles. We haven't done anything with them in algebra. First time. Assuming most of us have flown in a plane, right? You guys have flown in planes, yes? In the Midwest, you've flown east. So you're flying over like Kansas and Nebraska. You guys look down, and what do the fields look like? No? A lot of them are in the shape of a circle. That's interesting, huh? Do you have any idea why? Why would you build a field in the shape of a circle? Yes? Yeah, if you guys, have you probably seen these before? In fact, there's one out near the material recycling facility out here. And it's the irrigation device. It's a big truss system, and it's on wheels. And the water pumps in from this central point. And as the water's pumping in, these gears drive this big arm that swings around that common point where the pump is, and it creates a circle. And so that's how they water their fields. There's one of the ways you can water your fields. So that's why you use a circle. All right, so what's that have to do with this? Well, there's application to circles and some of the things that we're going to be doing. If you're manufacturing things, some things have circular pieces to them, and if you're talking about like surface area to how much plastic that you need to make this cup or to make this bottle, we're talking about formulas and forms. All right. So do you remember when we were talking about parabolas, we had this equation? Does that look familiar? Yes or no? No. Okay. That one was called, do you remember who that looks familiar to? What's that called? What's that one? Vertex. That's vertex or parabolic form. And when we graphed parabolas in this form, we were able to use h and k, and h and k told me the vertex of my parabola. Well, this h and k thing actually is used through multiple families of functions. So I can have this for a cubic function, I can have it for a square root function, I can have it for circles, I can have it for absolute values. The h and k thing is telling me how I locate a starting point, graphically speaking. Or in this case, for the vertex, finding h and k, where does that bottom or top part of your parabola happen? In the circle world, the h and k tells you where your center is. So it's the same concept. The h's are with the x's, and I'm within the parentheses here is something being squared. So I think opposite. So if I wanted to know what x minus 3 meant for my circle, it means go right 3. And then the k's are a little different because now the k's you see are lumped with the y's. And that means we're talking about up or down. So I can very quickly, based on the equation, tell where my center is. And once I know where my center is, I can draw a circle, find out what my radius was, and all that fun stuff. So when your h and k becomes 0, look at x minus 0 is x squared. Y minus 0, y squared. We just get this equation. All right, so formula sheets, right? If I'm a flashcard person or formula sheets, I put these in my formula sheets or flashcards. You're going to have to know these two equations. Be also paying attention to the fact that we are equal to a r squared. Does that formula look like something that we're familiar with already? What's it look like, Justin? Yeah, whose theorem is that? Good old Pythagorean theorem, right? So it looks like a squared, b squared, and c squared, and that's really what it is. It's a distance let's write equation. We're going to have to, here's a circle, let's find the equation, but also here's some information about the circle, let's find the equation. Or I could give you the equation and we can graph the circle, so we can be able to go all different directions with this thing. So our radius of 4 on the first one, center at -3, 6. So what I'd like you guys to do is identify H's and K's and then R's, and then from that we'll be able to draw our circle. So here's our H and K. Remember that the X value of the center is your H, and the Y value of the center is your K. So I know that H is equal to a -3, and K is equal to a 6. So when I go and write this in my equation, though, those become opposite values, because my equation is X minus H and Y minus H. All right, there's my radius of 4. So we have all of our parts. We have our R's, we have our H, we have our K's. That means we're able to write this equation. We need to move these down. Come down here. There we go. So we start out, I would say, probably start out with the generic, this one, H minus X, or X minus H squared plus Y minus K squared, R squared. And we only fill in, when we're writing the equation, we're going to fill in 3 things, H, K, and R. And so we have those. We have X minus -3, or X plus 3 squared, and Y minus 6 equals, now my radius is 4, so we're going to do 4 squared and get 16. So that's the equation of this particular circle. All right, let's see what it looks like. Hopefully it's a circle. How do you draw these things? Well, first you go to your center point, which in this case is -3, 6. We're going to go over to -3 and up 6. We're going to put a point. There we go. There's our point. And now from that point, we would just, if we had a circle template or a compass, right? We had a compass. You guys know what a compass is, don't you? You work with those in geometry, those things that kind of open like this. All right, so if I had a circle template or I had a compass, I could put the pointy part of the compass right there. I can extend the pencil part of the compass out 4 units, because that's what my radius is. So out 4 units, and then be able to draw my circle. So it's like saying, from this point, I'm going to go 4 to the right. I'm going to go 4 down. I'm going to go 4 left. I'm going to go 4 up. And then if I connected all of those, I would have my circle. It's clear. That's amazing. That is amazing. So here, let's see. There's my circle center point, and I go out 4, and bang. There. Oh, man. Yep. So there I am, circling my radius 4 units away from that center, all the way around. Yes, Al?
So what? Oh, wait. I was wondering what the equation.
Oh yeah, the equation.
That's just the equation for the circle.
That's the equation for that circle. So with the equation, we were able to draw the circle because I knew where I had to start it, and I knew how far I was from the center, and that's what helped.
So in this problem, you're not using the equation to find it. You already have the stuff. So
I have the stuff.
Into the.
Correct. I'm just using the information that they gave me to draw the circle. I didn't need the equation to do it.
Right.
But you could do it from the equation, right? Right. You could draw the circle from it. All right. What questions for that? Does that look pretty simple? Pretty easy? Yeah, this is the fun part when you get people doing homework on this stuff, because their circles are always weird looking. But that's all right. All right. Take a shot at the circles. Okay, here we go. Next one. Why don't you guys come up with the equation for that? And we'll have somebody up here draw it for us. Oh, that'll be fun. All right, you ready to do this? You ready to come up here and tackle the smartboard? Not literally, quite literally, because then I couldn't use it anymore. But if you could just. All right. So tell us, first of all, write the equation up there. Never have a chance to write the equation down, or am I going too fast? I can just talk to you. No, see, you won't even respond. Christina responds. She's like the voice. Oh, we're running out of room.
I respond all the time.
Huh? Wait, hello, what?
I respond all the time.
Oh, yeah, I guess you do sometimes. Sometimes you do.
Don't hear me.
Maybe I don't. Okay, is he right so far? Yeah, he is. He's right so far. That's nicely done. Now, draw a circle. This is the fun part. You just double tap on the points. All right. Yep, yep. Uh-oh. Somebody's phone part. All right, go ahead. Oh, that's not quite it there, my man. There you go. Hit it again. Hit it one more time. One more. Hit it. All right. Look at that. Oh my goodness. Giving us a headache. There we go. All right, now how do you draw a circle? So see to this. Yeah, perfect. It's already ready to go. Put your finger in the middle. Drag your finger. Wham! Does everyone want one of these in their bedroom? All right. There you go. Is that what you guys had? Okay. Good deal. So there we are with drawing circles, given information, writing the equation. So again, we're going to be able to do. See what happens. See, we're all nicely done. I should have hid those. So notice these guys have centers at 0, which means your h's and k's do not have to be, well, you could show them. Technically, you could say x minus h squared and y minus k squared. But if h and k are 0, we don't have to write x minus 0 squared and y minus 0. Now, what do you think in writing the equation? What do you think maybe a common mistake might be? Okay, yeah, that's true. So some people might put 0 in for x and y, but remember your h and your k is your center point. Okay, that's one mistake. What's another one that might happen? That has to do with the radius. What do you think people sometimes do with the radius? What's that? Yeah, they'll forget to square it. Exactly. So when you're writing your equation, don't forget to square the r value. Whatever that is. So those aren't going to be x squared plus y squared equals 4 and 3. They're going to be x squared and y squared equals 9 and 16. All right. Anyway, so we plot our 0, 0s, and then wham, here comes the circle. Hold on. There are centered at 0, 0. So. Okay, let's go the other way, though. Or wait, before we do that, maybe we can talk about wanting to find points somewhere else on our circle besides what we call the quadrantal points. These points, the ones that we were plotting and then drawing our circles through, notice that they are at, if you think of a compass, those points are at north, south, east, and west. And those we will call them our quadrantals. North, south, east, and west point. Or in terms of degrees, if we're thinking about, are you guys familiar with polar coordinates at all? Does that sound familiar? No? All right. Check out over here. It's a polar graph. Seen one of those before?
Yeah.
All right. Yeah, usually you shoot at with a gun or an arrow or something. Yeah, target. Okay. So this is called a polar graph. And polar is a way of finding a distance and a direction. And so you'll notice that the graph starts at 0 degrees to the right, and then it goes counterclockwise for its angles. 0 degrees, 15. Different from a compass, right? How many of you guys are familiar with a compass and how to use one? So a compass, where's 0 on a compass? It's north. 0 degrees is north on a compass. And then when you use a compass, do the degrees go right or do they go left when you go from 0 to, say, 90?
Go left. Right.
We go right. If you think of a compass, here's a compass. That's 0 degrees. East is 90. Compass south is 70. Compass west is 350. No. 2. This is 180. And then this is 270. So you go clockwise for a compass. That's called a bearing angle, and that's called over there a polar angle. So they start different places and they rotate differently. We'll get to those things later on. But you can refer to quadrantal points as being at the polar angle. So north would be actually at 90 degrees. South is actually at 270. East is 0. And west is 180. 0, 90, 180, 270, back to 360. So that's for polar versus a bearing, which is a compass. So we'll get a chance to talk about those later on down the road. All right, here we have this now. Let's write the equation from these. They don't look quite as just because I've got that square root thing going on there, maybe that throws you off. But don't let it throw you off. I still have a C. I still have a radius value. I should still be able to quickly write the equation. That's not that bad, right? Okay. Okay, I'm going to call somebody here. They're going to help me fill this in. All right, for that first one, tell me. Let's see, Mr. Ryan Rosa. What's the H value in that first one? So in my equation, it's going to be what? X minus 1. Okay, what's the K value? Brooke? In my equation, you mean? Yes, in my equation, it's plus 2. Okay, now here's the tricky one. What is my R? Oh, good, 7. So I square something being square rooted, I just undo the radical. Right? So if I square a radical, just get rid of the radical. And I have 7. 7, you guys ended up with? Yeah? So we're square root of 7, square root of 7 is square root of 49. Square root of 49 is 7. All right, so don't be panicked. What happens if we end up with a radius that's negative? Is that possible? You know, think about like a negative length of a circle. I really can't have that, right? I can have a direction that goes into the negative x values, but I can't have a negative radius. I can't draw circles with negative lengths. Do you have a question?
For the equation.
I forgot my squares. Is that what you're going to tell me?
But is it always going to be like an x minus something plus?
Oh, good question.
Like an x, is it always going to be plus?
Is there always going to be? That's a great question. Is this always going to be a plus? What do you guys think? Yes, that will always be a plus. When it's not a plus is when we get to chapter 12, and that's when we have things like ellipses.
Okay.
But we're talking about circles, so yeah, we'll always be a plus. All right, let's rock and roll here. We're going on some new stuff. So here now we go the other way. Here is the equation given to us, and now we want to find out parts of the circle. And we want, in this case, to find out what's our radius of the circle and what is our center location for this circle. So in this first one, x minus 3 squared plus y minus or plus 5 squared. Again, I have to just simply remember that the h's hang out with the x's, and the k's hang out with the y's. And then here's again, I'm going to be careful, that is not my r. 49 is not my r. 49 is my r squared. So remember, I need to change that to become just a radius. And then the other thing I need to be careful of is my h is just not what I see in the equation. Notice that this says minus 3 in my equation. So in my actual value of h and k, I'm taking the opposite of what I see in the equation. So this is actually a 3 for my h, and a negative 5 for my k. And there is the center of your circle. And then if my radius squared was equal to a 49, then I just square root it and get the radius is equal to 7. Now again, because I square root it, doesn't mean I take plus and minus 7. Because again, we're talking about distance, and so I can't have negative distance. We're going to just talk about positive 7. So there you are. There's my radius, there's my center from my... All right, quick. Sophia, center point for the next equation there to the right.
Negative 7, 9.
Negative 7, 9. And then radius, Mr. Booth.
The radius would be 10.
Yes, sir. There it is. Negative 7, 9 radius. Do you think your radiuses can be decimal values? Is that okay? Sure it is. Yep, radius can be a decimal value. It doesn't have to be a nice whole number there. All right. Any questions so far? Does it seem pretty simple? Okay, good deal. And what about here? What about that? Now that is an equation that is looking really funky. So the ones that we were doing before, these x plus minus some value squared, and then y plus minus some value squared equals some r squared. That's what we call standard form. But sometimes we have circles that are not in standard form. So these two equations right here are circles. But they just don't look like what we're used to seeing. And then what we have to do is we have to use completing the square. And in this case, because I have two variables, x's and y's, I'm going to have to complete the square twice. Once for the x's, once for the y's, and then I'll get something, x minus something squared, and then I'll get a y plus or minus something squared, and then I'll have some constant on the right that becomes my radius squared value. So, do we remember completing the square? You guys remember how to do that? So long ago. That was a while ago. So here's what I'm going to suggest you do on this. So here's our steps. Get the equation in standard form, which means, again, standard form is x. I'm just going to write minus, but it could be x plus. So x minus h, y minus k squared, r squared. That is standard form. So we're going to take the x values, x squared and 6x, and we're going to complete the square with those values. Then we're going to take the y value, y squared and negative 4y. We're going to complete the square with those two. Now that 23 is actually a good spot. It's already hanging out where it needs to be. It's already on the other side. That's our constant. That's our c value. So let's see if we can remember, refresh our memory here on completing the square. You get an opportunity to do it twice for each of these problems, so you're going to be good at this by the time we're done with circles. Okay, so let's look at x squared and 6x, and we're going to complete the square on this thing. So right now I've got a 23 that's hanging out over here. All right, help me. What do? We've already taken care of our first two steps. our next step be, Sam?
So, half 6 and squared.
Half of b is squared. So half of 6 is 3. That answer goes right here, and it goes over here. Remember that? Will this answer be negative ever? Never. It'll never be negative. So b over 2 squared, squaring something always be positive. So 6 over 2 is 3. 3 squared is a 9. So 9 here. All right? There's completing the square with the x's. Now we go do the same thing with the y's. We have a y squared and a negative 4y. And we're supposed to add on to that. And we're supposed to add on to the 23 something else. What are we going to get? 4, right? Half of negative 4 squared is negative 2 squared, which is 4. We're adding that to both sides. Okay. So here's the only thing we've got to be careful. Remember, we're not treating this as two separates. We're actually working them together. So what I really need to think about is I've got that 23. That 23 is, there's only one 23. I just set it up this way to show completing the square. So really, I'm not going to go 23 plus 9 and then add on to that 23 plus 4, because I'm counting the 23 twice if I do that. So really, the only thing I'm adding is what? To the right-hand side. I'm only adding those two together, which means I'm adding 13 to the right-hand side of the problem. And so what would my equation look like? Well, we've now got this. We have the red, which becomes binomial squared y's, becomes what? What is this going to become if I write it as a binomial square? X plus 3, good. Remember, we just take whatever b over 2 is what goes in that second spot. We've got x plus 3. Do the same thing with my y's. Square form, binomial square form of y squared minus 4y plus 4 becomes y minus 2. All right? And then that's going to equal our 23 plus our 13. So now we have our correct form. X plus 3 squared, y minus 2 squared, and then 36. So now you're back to standard form. There we go. What questions do you have for that problem? Practice. Good stuff. Nothing? All right, you guys do the next one. Try that one on your own. See what we get. X squared minus 2x plus 1. What's that? Y squared plus 8y plus 16. So I'm adding 17 on the right-hand side. And so it looks like we're going to get...
Oh, for each one?
Yeah.
So this is like x minus 1 plus x plus 4, or y plus 4.
Yeah, yeah. And then equals 25. Is your answer
So it's good.
I think Miss Christina was correct. She was ready to go. Go to blows over that one.
Yeah.
X minus 1 squared y. So for those of you getting a different number, what happens? Random number. You mean you just made up a random number just because?
I don't know what slow it down.
Because it is especially possible.
Oh, okay, so you just have a little brain lapse there, a little brain fart.
Square, yeah.
Alright.
Square root is just.
Simon, you good? Figure out where the 25 comes from? Alright. Alright, any issues on those? That's probably the hardest thing we're going to do with this stuff. Is complete the square root and find our standard form. Alright, I think maybe we should take a little stretch break and then we'll come back. So a little while ago we talked about sometimes I'm going to be finding points along the circle that are not on those 4 special locations. You guys remember what the name of those 4 special locations was? What were they? Quadrantal points. All right, so sometimes we're going to have to find points that are elsewhere. And in order for me to do that, I'm going to use the distance formula. So again, distance formula, refresher 101. Where does it come from? Who's near? Pythagoras. Right? Comes from a squared plus b squared equals c squared, right? And what we do with it is we just translate the a squared to b squared part as the difference between 2x values of a point and another point, and the difference between the y values. So let's see what that looks like here. Negative 3, 5. Here's negative 3, 5. And then negative 2, negative 8. Negative 2, negative 8. We get those 2 points. So why does the distance formula look like this? Distance equals to the square root of delta x. Delta is the same thing as difference. It's the same thing as saying x2 minus x1. And then this can be delta y. Then we square those. So how are we getting that? Well, remember the a squared and the b squared part? That's where the squared thing comes from. So we get these 2 triangles, these 2 points, and they actually create a triangle. It's kind of a hard one to see, but So I have, in terms of an x difference, I have between here and there is the difference in my x's from one point to the next. And in terms of the difference in my y's, I have from here to there. And those 2 would then be connected with a line that creates this distance that we're looking for. This length between those 2 points creates this hypotenuse of this triangle. And that is why we're using Pythagorean theorem. Because we have an x value on a leg, we have a y value on this leg, and we're trying to find out how far is it between them. Well, we're just looking for the hypotenuse, that's all. So when we go and when we think about our normal a squared, b squared, c squared thing, and we're saying, well, we're going to go from x1, y1 to x2, y2. This a squared distance is just taking the difference between the x's and squaring them. And this b squared is just taking the difference between the y's and squaring them. And that's how we get our c squared value, or in this case, our distance. All right. So I'm applying this principle here. And yeah, here's another formula, right? So 3 of them so far. We're adding to our formula sheets. Standard form of a circle located other than the origin, and now distance formula. D is equal to the square root of x2 minus x1 squared plus y2 minus y1. So we apply that principle here. Now, does it matter what one I call x1, y1, x1, x2, y2? Is that important? No, some are shaking your head no. So this one could be x1, y1, and this one could be x2, y2, or I can flip them. What will matter though? What's a no-no?
If you have, so if you have like 3 or negative 3, I don't know.
Yeah, no, you're right. Negative 3 can't go with which one?
With
The negative 8.
Yeah.
The negative 3 and the negative 8 don't work together because they're not x1s, y1s, or x2, y2s. So you have to have the same pairing work. So again, it doesn't matter if negative 3, 5 is the 0.1, or if negative 2, negative 8 is 0.1. That's not a big deal. But it is important that we just call one of them x1, y1, the other one x2, y1. All right, so we put that into our distance formula here. Plugging it all in, we get a negative 2 minus a negative 3. So here's where you got to be careful. Negative 2 is x2. We're subtracting a negative 3. And then we're going to square that difference. And then we're going to do the same thing with y. Start with a negative 8. And we're going to subtract a 5. We're going to square that. And all of this is still hanging out under the root, the radical. So these numbers, once we square them, will always be positive. So a negative 2 minus a negative 3 actually becomes a negative 2 plus a 3. This becomes a negative 13. So we get a 1 squared, 1, plus a 13 squared, 169. And all of this is under the square root. And so we can make the statement that the distance between those 2 points is the square root of 170. Now here's what I want you to do with distance formula. I don't want you to convert it to a decimal unless we're graphing it. I want you to either leave it in radical form, well, you leave it in radical form simplified. So what do I mean by that? So 170. If there is a perfect square as a factor of 170, like 4, is 4 going to 170? No. Does 9 go into 170? No. 16? No. All right. So there's nothing that goes into 170. I wouldn't be able to write it in simplified radical form. So I am okay that you actually leave your answer like that. As long as it's simplified, you're good. Now this distance, we're talking about units. We don't know if it's inches or feet or centimeters or whatever. So we're going to use units. We don't know what it is. So that's the distance between those 2 points. Square root of 170, which is just over 13. Just longer than 13. So I can use that then to find points along my circle. Anywhere along my circle. Right, that's just a refresher on the distance formula. But let's actually use it in a circle and see how we can apply this. Yeah. So here we have 3 points. And we're going to somehow prove that that thing is a right triangle. With just knowing coordinates here. I don't have any other information. So we know what the coordinates are. We connect to those points. We get this triangle. And we look at that triangle. And you might want to say, hey, it looks like it's a right triangle. It looks like maybe this corner down here is a 90. But we don't want to make an assumption that it's 90. We actually would have to prove that it's 90. Now, notice that the question was that these given points are the vertices of a right triangle. There are actually 2 ways I could tackle this problem. Does anyone have an idea of the first way we might be able to do this? It's different from my hint here. Okay, that's what we're gonna, with this one, we are gonna use the distance formula. That is one way, yep. There's another way that I can see if it's right. Chapter 1, we work with this stuff. Yep, slope. Yeah, how would I use slope to prove that this is a right triangle? Any brainstorms? Yeah, if they're perpendicular. And how do we prove that 2 lines are perpendicular? You're right, you're on the roll. You're on the rolls. Anyone want to help him? Two lines are perpendicular if their slopes are what of each other? Not just reciprocals. Negative or opposite reciprocals. So it looks like the two lines that are 90 degrees are line AB and line AC, or line segments AB and AC. So what I could do is I could just use the coordinates they gave me and find the slopes of those two things and happen to see if they are opposite reciprocals of one another. That's one way we could do this problem. But if I want to use the distance formula, then what am I after? How am I going to prove that this thing is a right triangle using distance formula? Think about the legs and the hypotenuse. What must be true about them if this is a right triangle? That's right. Yeah. If it's a right triangle, then that would mean this leg we'll just call for right now A. And this leg we will call B. If I squared them and added them together, they would equal, again, we're going to call that length. It's just saying, let's test the distance formula and see if these A squared plus B squared actually give me AC squared. So that's the second method I could use to calculate whether or not this thing is a right triangle. Not having to do anything with slope. Just doing something for distance. All right, so here's what we're going to do real quick. See if we can make this work. So let's say this little path right here. And then you guys are going to find A. You guys go back over there. You're going to find B. And you guys are going to find C. Yeah, so you guys are finding that. Back in the back, finding this. You guys in the front, finding this. And then let's see if we put them together, do we actually get a right triangle. Does everyone see the coordinates? Does everyone see the coordinates okay? You guys are trying to find this length C here. Yeah. So you're trying to find the length. Trying to find the respective length. Okay, so my A's told me, what was it again, A's? 4 root 5, which is square root of 80. All right, B's, what did you guys get? 5 root 5, which is square root of 125. And then C's, I'm sorry, I forgot the C. Square root of 205. Okay, so if we're going to see this thing being a right triangle, that would mean if I squared A and I squared B, and I added them together, I would get C squared. Let's see if that's true. Is A squared plus B squared equals C squared? That is the question. So we're going to leave them in our just radical form here. So square root of 80 squared plus square root of 125 squared. Does that equal the square root of 5? Yes, squared. Yes, it does. 80 plus 125 equals 205. That is true. Check. Therefore, it's a right triangle. Voila. So there we are using distance formula. Again, you could have used slope. That's another way. All right. I'll leave this. We'll stop here on this one. I think this might have been a homework problem. Challenge. So, any questions before we roll on? Yes. Go back. Yeah.